In this episode, we're going to unpack virtualization in a way that feels simple and concrete, because virtualization is one of those foundational concepts that shows up everywhere in modern computing, including on-premises environments and cloud environments. If you are new to cybersecurity, you might have heard that virtualization provides isolation, and you might assume that isolation automatically equals security. Virtualization can improve security in some ways, but it also creates new kinds of shared risk, and that tension is what makes it important to understand clearly. At its core, virtualization is a way to run multiple logical systems on top of shared physical hardware, and it relies on software layers to divide resources like processing, memory, storage, and networking. Those layers can enforce boundaries, but they also become critical control points that attackers may target. The security implications are not just about whether one virtual machine can see another, but also about what happens when the shared foundation is misconfigured, overloaded, or compromised. By the end of this, you should understand what virtualization is, why isolation is both real and limited, how shared resources create risk, and how these ideas show up in practical security thinking. A good way to start is to define virtualization in plain language as the abstraction of physical computing resources into flexible, software-managed pieces. Instead of one physical server running one operating system, virtualization allows one physical server to host multiple separate operating systems, each believing it has its own machine. The software layer that makes this possible manages the hardware and presents virtual hardware to each guest system. This is powerful because it improves utilization, allows rapid provisioning, and enables easier management and recovery. For security learners, the key is to see that virtualization changes the boundary lines in an environment. The boundary is no longer only the physical box. It becomes a logical boundary enforced by the virtualization layer. That means security depends on how well that enforcement works and how well it is managed. It also means that a single physical failure or a single misconfiguration can affect multiple logical systems at once. Virtualization is therefore both a scaling tool and a concentration of risk tool, and learning to hold both truths at the same time is an important step in becoming a mature security thinker. Isolation is one of the main reasons virtualization is attractive, and it is also one of the most misunderstood concepts. Isolation means that each virtual machine, or each isolated environment, is meant to behave as if it is separate from the others, so that one system's problems do not automatically become everyone's problems. For example, if one virtual machine crashes, others can often keep running. If one virtual machine has a misconfiguration, it does not necessarily mean the others do. From a security perspective, isolation is meant to limit what an attacker can access after compromising a single workload. However, isolation is not magic, and it depends on correct configuration, strong management access control, and a trustworthy virtualization foundation. Isolation also has practical limits because systems still share underlying hardware, and because administrators often connect those systems through shared networks and shared storage for efficiency. For beginners, the key idea is that isolation is a benefit you can strengthen through good design, but it is not a guarantee you can assume without verification. To understand why isolation can be limited, it helps to see virtualization as a set of layers, where each layer can either reinforce boundaries or weaken them. At the top, you have the workloads, which are the guest operating systems and their applications. Beneath them, you have virtual devices and virtual networks that create the illusion of separate machines. Beneath that, you have the virtualization control layer that schedules resources and enforces separation, and beneath it you have the physical hardware that everything ultimately uses. If the top layers are isolated but the control layer is misconfigured, an attacker might move between workloads through shared network paths or shared credentials. If the control layer itself is compromised, isolation can collapse because the attacker now has a position underneath the workloads. For beginners, the important point is that the virtualization control layer becomes a high-value target because it sits in a privileged position. The more workloads depend on it, the more valuable it becomes to attackers. This is why securing management access and minimizing administrative exposure is so critical in virtualized environments. Shared resources are the other side of virtualization, and they create security implications that are easy to miss if you focus only on isolation. When multiple workloads share the same physical processing and memory, a problem in resource allocation can become a security and availability issue. If one workload consumes too much processing or memory, it can starve others, which can lead to degraded performance or downtime. This is often thought of as an operational issue, but in security terms, availability is part of the security mission, and resource starvation can be triggered intentionally or accidentally. Shared storage creates another set of risks because multiple workloads may rely on a shared storage system, and access controls must ensure that one workload cannot access another's data. Shared networking also creates risk because virtual switches and virtual network segmentation must be configured correctly to prevent unauthorized access paths. For beginners, the key is to recognize that sharing creates dependency, and dependency creates cascading failure risk. Virtualization concentrates multiple systems onto fewer physical foundations, so when something goes wrong at the foundation level, the blast radius can be larger. A practical security implication of shared resources is that the virtualization environment often becomes a place where misconfigurations can have outsized impact. For example, a misconfigured virtual network can unintentionally connect systems that were meant to be separated, creating a path for lateral movement. A misconfigured storage permission can expose sensitive data across workloads. A mismanaged snapshot or image can preserve secrets longer than intended or replicate sensitive data into places it does not belong. Even though we are not getting into step-by-step implementation, it is important to understand the concept of sprawl, where virtual machines and images accumulate quickly because they are easy to create. Sprawl can create unmanaged assets, which then become unpatched and unmonitored, and that is a classic risk pattern. Another implication is that shared management systems can become a single point of compromise if administrative credentials are weak or widely shared. For beginners, the lesson is that virtualization makes it easier to build complex environments quickly, which is great for agility, but it also makes it easier to accidentally build complexity that security cannot see or control. Another important concept is that virtualization can change how you think about trust boundaries and what it means to secure a host. In a traditional environment, you might secure each physical server independently, and the physical boundary gives you a simple mental model of separation. In a virtualized environment, the physical server, often called the host, runs many workloads, and securing the host includes securing the virtualization control layer, the management interfaces, and the networks and storage systems that connect everything. If the host is compromised, an attacker may gain access to multiple workloads, not because those workloads are weak, but because the attacker now sits underneath them. That means the host and its management plane must be treated as high-sensitivity assets, often more sensitive than any single workload. For beginners, it helps to think of the host and management plane as the building's foundation and master key system, while the workloads are the individual apartments. If you protect only the apartments but leave the master keys exposed, isolation will not save you. This is why identity and access management for virtualization administration is so crucial. Virtualization also influences monitoring and investigation, because the evidence of activity may be spread across both guest systems and the virtualization layer. If something suspicious happens, you may need logs from the guest operating system, from the virtual network layer, and from the management plane to understand the full story. For example, a guest might show suspicious authentication, but the virtualization layer might show that the guest's network connectivity changed or that a snapshot was created unexpectedly. This matters because attackers who gain administrative access to the virtualization layer can sometimes manipulate workloads in ways that are not visible inside the guest. For beginners, the key point is that visibility should match the layers of your architecture. If you monitor only inside the guests, you may miss privileged actions taken beneath them. If you monitor only the host layer, you may miss application-level impact. Effective security treats virtualization as a multi-layer system where logs and controls must exist at multiple points to be meaningful. A common beginner misunderstanding is thinking that virtualization automatically equals strong segmentation because virtual machines feel separate and because the word isolation is used so often. Real segmentation requires deliberate design of networks, access control policies, and administrative boundaries. Virtualization can make segmentation easier to implement, but it can also make it easier to accidentally connect everything through convenience choices, like shared networks and shared administrative access. Another misunderstanding is thinking that because virtual machines can be restored or rolled back, security problems can always be undone. Snapshots and rollbacks can help recovery, but they can also preserve vulnerabilities and secrets, and they can hide the true history of what happened if used carelessly during incident response. Another misunderstanding is assuming that if a guest is compromised, the host is automatically compromised, which is not always true, but the reverse risk is often more dangerous. If the host layer is compromised, many guests are at risk. For beginners, the takeaway is that virtualization changes the risk landscape, and you need to think about which layer is being protected and which layer is being trusted. When you bring all of these ideas together, understanding virtualization for security means understanding both the promise of isolation and the reality of shared foundations. Virtualization allows multiple workloads to operate independently on shared hardware, and it can support stronger security when boundaries are designed well and management is controlled tightly. At the same time, shared resources create concentrated risk because a failure or compromise in the underlying control layer can affect many systems at once. The security implications include the need to protect the management plane, to design segmentation intentionally, to control sprawl, and to monitor across layers so investigations can see the full story. For beginners, the most important lesson is to resist simplistic conclusions like virtualization is always safer or virtualization is always riskier. It is a powerful architecture approach, and like all powerful approaches, it can be used well or poorly. If you understand how isolation works, how shared resources behave, and where control points concentrate, you can reason about virtualized environments with clarity and make better decisions about what to protect, what to monitor, and what to prioritize as risk grows.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.